Large-scale deployment of unmanned aircraft, or drones, is going to transform the way we live and work. Drones can be used for package delivery, security patrol, traffic monitoring and many other tasks. They will become an integral part of the smart city infrastructure. Due to hardware limitations, small multi-copter drones are unable to conduct pre-flight physical checks on their own. Pre-flight safety checks involve detecting various anomalies, such as imbalanced payload, damaged propellers, malfunctioning motors and poorly calibrated compass. Human efforts are required for performing such tasks, which impedes the large-scale deployment of drones and increases the operational costs. To close this gap, we invented a smart lending platform that handles pre-flight checks automatically for small multi-copter drones. We designed a digital scale equipped with multiple load measuring tips beneath a flat and rigid platform surface with grid holes. The platform is able to measure the weight and weight distribution of any unmanned aircraft that lands on it. During diagnosis, when a motor spins at a given output level, the propeller, if in good condition, is expected to generate a calculable amount of upward lift, which would lead to a reduction and a redistribution of the aircraft weight as sensed by the platform. By analyzing the instantaneous weight measurements within a statistical computing framework, anomalies in payload distribution, actuation, propelling and navigation subsystems can be detected and properly attributed. We developed a nonlinear least squares model with airframe geometry constraints to analyze the measurement data and draw accurate inferences. Since the load cells are able to take instantaneous measurements quickly, a large amount of samples may be recorded in a short amount of time. As the sample size increases, it becomes increasingly difficult for an optimization solver to find the global optimal solution within a practical time frame. To overcome this difficulty, we derived a closed-form analytical solution to the nonlinear non-convex optimization problem and proved the uniqueness of the solution. As a result, the computing time is reduced from many minutes to a few seconds. The effectiveness and practical value of the proposed platform and algorithms are validated through an extensive set of experiments. The proposed apparatus and the diagnostic model can be integrated with other innovations aimed at increasing the level of automation in drone-enabled systems.